In my first Introductions to Systems video, we looked at several systems I encountered on a block, and we addressed the following points. First, a system is a volume that contains a matter of interest. It may have an obvious boundary, like a reactor, or it may have a more ambiguous boundary. You get to decide the boundary suitable for the problem you're trying to solve. Systems can be open or closed. In an open system, matter flows across the system boundary. Finally, a system may be natural, like a tree, or an engineered system, like a city's sewage system. Some systems are a combination of both. Now I want to take those systems we talked about and make some simple diagrams. If you need a refresher on that last video, you can reference the link in the description. Engineers use diagrams to represent systems. These diagrams are also called process diagrams or flowcharts. We can use relatively simple diagrams to represent the four systems we viewed on our block. When you make diagrams, remember that you don't need to be an artist. A simple diagram is a clear diagram. Draw the simplest diagram that you can to convey the important parts of your system for the problem you're trying to solve. Let's draw out our four examples. For the puddle, you can draw a circle or a square. It does not need to represent the shape of the puddle. The edge of that circle or square denotes the system boundary. If we're considering a puddle a closed system, then you don't need to add any matter flows into or out of your system. If you're considering any reactions in that system, then you can note those on your diagram. For example, for our puddle, let's make a note about algae growth. For our tree, we can draw a simple shape. Here is a rectangle. Then let's draw the flows into and out of that system. Which flows you choose to consider is going to depend on the system and the question you want to answer. For example, if you're concerned with the tree's impact to the water cycle, you could include water flows into and out of the tree. But unless you're doing a very detailed model, you probably don't need to worry about the reactions of the enzymes or the enzymes in the tree, or where exactly through the tree the water is flowing. Only include details relevant to your problem. Otherwise, your model could get unnecessarily complex and confusing. When we draw systems like this tree, we start to consider the tree like a black box. This is a very important engineering concept. While there's a lot of complexity and several processes occurring in the tree that are not important to our problem, we can ignore those. We can learn a lot by considering the tree as a black box, looking at inputs and outputs, and ignoring the complex biology of the tree. Doing so will help us simplify the problems so they're easier to solve, and in some cases, this can make problems possible to solve. For the Berkeley pit, we can do the same thing. Here's a diagram of the pit, the groundwater flows, evaporation, surface water flows, and engineered flows from the mining operations. Note how the arrows denote the direction of water flow into and out of our system. Finally, for the stream, we can draw it as a line or a rectangle. The stream will draw as a line or a rectangle. In general, you will want to stick to simple diagrams that represent the systems. The aspect ratio, that is the length of the stream, being much longer than its width, is important for many stream functions. So the elongated aspect ratio of the line or the rectangle denotes that important feature of our system. And then we'll put some matter flows across system boundaries and any reactions that might occur. So that concludes our introduction of systems. We discussed diagrams, also called process diagrams or flowcharts, which are how engineers depict systems in technical drawings. Finally, we discussed the idea of a black box, where you simplify a system, consider only the inputs and outputs of that system, and any relevant reactions in the system, while ignoring the details and the inner workings of that system. This simplification will help you solve many engineering